Okay, welcome students. This is a short video for the calculus class about one major aspect of the study of calculus, and that is the derivative. We'll explore that idea together. Okay, students. So here I have a function. F of x is equal to x squared, and in this function I have the curve is graphed right here. And I have a line that's joining 2 points. Now remember, on a circle, a line through 2 points on the circle forms what's called a secant line. And this blue line is my secant line. Now, let's just make believe this has to do with someone driving, and it shows their distance away from home at a certain time. So again, this point right here is this point B would be representing values. Let me put the coordinates over here so you could see it. So again, point B, what we're saying is, like for example, notice here at 0.6, let's say minutes after I left home on 0.36 miles. Okay, you get the gist of what I'm talking about. Now, let's just say that I'm going to get close to 1 here, right? Okay, and I want to start between 0 and 1. Notice that my average rate of change is the slope of this blue line. So it's my average miles per minute, if you would, okay? If you want to think about it that way. Now, obviously, the further I go, the slope is getting taller, right? That makes sense, okay? And the further I bring this back to where I started, the more shallow the slope, so I wasn't going very fast, okay? So hopefully that makes sense. You could buy into that idea. Okay. Now, where we could use calculus is, calculus involves the idea of just not an average rate of change. We could use pre-calculus or even algebra for that. But here's something that's very, very interesting. If I bring, I'm going to imagine I'm drawing a tangent line, okay? I'm just going to imagine that. And remember, a tangent line on a curve is just a point that only touches the circle at one point, on a circle. Now, notice here, you're not seeing the two different points. They look like they're the same point. And also, if you pay very close attention, you could see the slope here is changing all the way through here. And so the point, no pun intended, is that we could determine the instantaneous rate of change at a point if we knew the slope of the tangent line to the curve at that point. Now, what we probably need to do is just blow up a part of this curve so everybody can see it a little bit better. Okay, does that make sense right here? Okay, so here's our secant line, and now what we're going to do is we're going to use some algebra to figure this problem out, which is exciting. All right, let's do the algebra. Here we go. I need my pen here. Here's the function f of x is equal to x squared, and remember we're trying to understand how to set this up. So here's my curve, if you would, okay, and then I have a point here and a point here, and have this line that goes through there. Now, let's call this point x sub 1, and we can call this point x sub 2. Let's call this distance between those 2 points delta x, okay? Now, the y value here we'll call y2, and the y value right here we'll call y1. Now, according to the slope formula, slope is equal to y sub 2 minus y sub 1 over x sub 2 minus x sub 1. Okay? Well, now we know down at the bottom that the difference between x sub 2 and x sub 1 is just delta x. okay? And we know that the y is just a function. It's a function x squared. So we put a value in, we get a value out. So what we could do is we could use the idea of slope and do what is called the difference quotient. Now I know you've seen this before, but now we could actually use it, which is exciting. Now the difference quotient is just a change in the y over the change in the x. The first y is y sub 2, so it's x sub 2, which is x sub 1 plus delta x, that's where this came from, and minus f of x, which is just that y1 right there. Now what is our function in this case? Our function is x squared. So plug in, right, plug in to the function whatever is in parentheses here. So here we go, x plus delta x squared, right, minus f of x, which is x squared, all over delta x. Okay, so this is an algebraic representation of the slope of this line. Okay, let's do a little manipulation. Everybody knows that's x squared plus 2x delta x plus delta x squared minus x squared. And this is all over delta x. Now we clean this up, the x squareds go away, and of course delta x goes into delta x into delta x one time, delta x into delta x squared, delta x time. So now I have 2x plus delta x, okay? Now remember, calculus involves some pre-calculus formula, a limit process, and some new formula, or we can call it calculus. In this case, we want to do what is the limit of 2x plus delta x as delta x gets closer to 0. Right, closer to 0. We want to take this distance between these 2 points up here, and we want to make that 0. I want to bring that point so close to the other one it's right over it. And that's what I was trying to do with making that tangent line. Well, folks, algebraically, we could just plug in, right? We could plug in 0 for delta x. And so what is that? It's 2x plus 0, which is just what? 2x. Now, this is called the derivative. And what that means is this represents the slope. This represents the slope of the tangent line at any point on the curve. Now, let's go back to our demonstration and see how this works. Okay, so we're back at our illustration here, and now you notice here I could take my point A, and we're looking at the slope. Here's the slope here, right? 1.10. We want to actually do the tangent line. So let's pick a value that makes sense. Here's 1. Okay, 1. So you could see it down here at the bottom. You can also see it on the coordinate. Now, according to our derivative 2x, the slope of the tangent line at point B should be 2 times 1, which is 2. And now take a look over here. Notice what's happening with the slope. Okay, I can't get the tangent line, but I can get mighty close to the tangent line. See that? 2. That's really incredible. Let's go back here and let's actually pick another point that's a little bit maybe harder to see. Here's point 7. Okay, what would the slope of the tangent line be at point 7? Well, let's just run this up here, and lo and behold, I'm right at there, and it's 1.0. Now that is actually very incredible. You can actually figure out the slope of the tangent line anywhere along the curve. Now this could represent a car traveling. It could represent money. It could represent a lot of things that change over time or change with a changing domain value. So I hope that made sense, that you could take a function, you could take the derivative using a limiting process, and then what you could do is you could see how it works in a real life situation. That's the power of the derivative. So many applications of the derivative. One would be to try to maximize function, and one would be try to minimize the function. A great example would be a car. You want to maximize the mileage. You want to maximize the power output. You want to maximize the comfort. You could go on and on and on, and you want to minimize the cost. You want to minimize the air drag. We could spend an entire day just talking about the automobile. Actually, we could just the engine itself, we could take an entire day and talk about. So this idea of the derivative is very important in the study of calculus, and I hope you enjoy learning about it.